So I got a few questions after last lecture about kind of what physically we're doing when we do these rotations, okay? And so the idea is that we have three principal stresses. And actually, if we're gonna have a right-handed coordinate system, then it has to be S1, S2, S3. So we have these three principal stresses, okay, and they're the ones that are easy to measure, estimate, or infer, okay? And we talked about, at least with the vertical stress, how to estimate it or measure it, and soon we'll talk about how to get the horizontal stresses, or at least the minimum horizontal stress, and the type of tests that we do to try to estimate or infer that stress magnitude and direction, okay? So these are the three principal stress directions, and those are the ones that we can either measure directly, we can estimate, or we can infer it somehow, okay? But they're sort of arbitrarily oriented in the sense that we kind of need to have a true reference frame, right? Because these coordinate frames, there's an infinite number. We can just choose one. We're modelers. We can choose a frame that's of reference, that's of interest to us. For example, this is just a little aside example. If you and I are riding in a car, right? If you and I are riding in a car and we're driving 80 miles an hour down the road, okay? And I ask you to tell me, say there, I have my cell phone sitting on the dash. We're driving 80 miles an hour, and I ask you to tell me how far is my cell phone away from me? Right? And let's say it's an arm reach, 3 feet or something, okay? Well, you have to choose a reference frame, right? In that case, I said from me, so in that case, the reference frame would be me, okay? But we're in a car driving 80 miles an hour, so we could choose a different reference frame, my house, right? And so in the car, you'd say, well, your phone is 3 feet away from you, right? But if you choose a reference frame to be your house, then it's 6 miles. It's 6 miles away from your house, right? So your choice of reference frame is arbitrary, okay? And we do it for convenience. Obviously, if we're in the car, it's convenient for you to say it's 3 feet away from me, and not try to figure out how far it is from my house, right? Okay, so we choose a reference frame that's convenient. Well, it turns out the one in a geologic setting that's convenient is the one that's always the same. So north, east, down, right? So this is our most convenient reference frame in a geologic setting, okay? And so what we do with these rotation matrices, they're nothing but geometry that take us from the principal stresses, the ones that are easy to measure. Wow. So these rotation matrices take us from the principal stresses that are easy to measure, infer, or estimate back into the geologic reference frame, which is the most convenient because it's always the same everywhere, right? North, east, south, and down. Now it turns out a lot of times that the vertical stress is actually exactly in the vertical direction, or down. So we can define an angle here, gamma. A lot of times that angle is actually 0, right? And so then those two are aligned, and then it's just a rotation in the plane, okay? And so then those others, I don't want to write them on here because I don't want to get them wrong and confuse you. I want you to refer back to the notes. But there were two more angles, okay, and one of them was what, alpha and beta? Yeah, okay. So one of them was alpha and one of them was beta. And I'm not going to draw them on here because I actually don't remember which one is which, okay? Just look in the notes. And on the first slide from the last lecture notes, it should tell you which one those are. So that's so that's all we're doing is the rotation matrices take you from one coordinate system to the other, okay? And in this case, the one we talked about last time was from the principal stress to the geologic, from the principal stress directions to the geologic reference frame, all right? And the reason for that is then now we want to find out what the stress is on a fault, and it's easy to describe the fault in terms of the geologic reference frame, okay? And then that's where those unit normal vectors and stuff came from. So we're going to do something similar today with respect to deviated well bores. So there's going to be another coordinate system now we're going to introduce, and it's a coordinate system that's going to be conveniently described within the well bore, okay? And since I think maybe it was not clear last time where the rotation matrix came from, we'll actually go through all the steps and derive it this time, okay? So here we have, basically what I'm describing. We have a coordinate system that resides within the well bore. So ZB, and it's labeled here, but ZB is vertically along the well bore. XB, it's a little bit hard to, XB is orthogonal to ZB and points in the direction of the bottom of the well, with the azimuth of the bottom of the well with respect to the geographic coordinate frame, north, okay? I'm gonna draw this, I'm gonna break this down in a second and it'll be a little more clear, okay? And then YB is just the one that's orthogonal to those two. Okay, so we're going to use the subscript B to identify the coordinate frame within the well bore. Okay, and we're going to refer it back to the geologic frame. Right? So let's look down the top of the well bore. So we're going to look down the well bore. And there we're going to have a coordinate frame that's the geologic coordinate frame. So I'm going to use X or north, okay? And Y is east, all right? And then we're going to have our well bore, and actually I'll use a different color for this. So our well bore coordinate frame, well, I'm sorry, this is not the well bore coordinate frame. I'm just going to say that there's another coordinate frame, X prime, Y prime, that's rotated from the geologic coordinate frame by delta. Okay, so I look down the well bore and I know where the geological coordinates are, and then I'm just going to create a new coordinate system, X prime, Y prime, that's rotated by theta from the geographic coordinate system. Okay? So if I then write That's hunched over a lot. Okay. So now my objective is I want to write x prime, y prime, and by the way, z prime is into the page, and z prime and z coincide. So the rotation is about z. Okay. So z prime is looking down. All right. So I want to write x prime, y prime, z prime in terms of x, y, and z. So x prime is equal to what? You remember what I told you last time about shadows, right? So I want the shadow of x prime on the y-axis and on the x-axis. I think you guys know it. Somebody say something. It would be, yeah, x cosine delta x, and then sine delta y, right? So cosine delta x plus sine delta y, right? So that's the cosine delta x is the shadow of x prime on the x-axis, right? And sine delta is the shadow of x prime on the y-axis, right? Y prime is equal to what? What's the shadow on the x-axis, which is actually the negative x-axis? So negative sine delta x plus cosine delta y. All right? And z prime is z. Okay? Now, for reasons that will be made obvious in a second, let's write this, and it's the reason I taught you guys some linear algebra. Let's write this as a matrix equation. Okay? Everybody okay with that? All right. So now, let's look at a little section of our Wellbore. Where now we have ZB, which is in fact down the actual, we have Z prime. All right. And I'm going to draw a Y prime like this, and X prime like this. So X prime, Y prime. All right. So we had our original Wellbore, which was perfectly aligned with the geologic coordinate system. And then we defined a new coordinate system that was some angle of rotation, delta, from that. Okay? So now we're going to take this new coordinate system and we're going to rotate it about the Y prime axis. okay? So in other words, what we're doing is we're going to rotate our wellbore okay? We're going to rotate our wellbore, and now we have a coordinate system where ZB is along the wellbore axis, and this angle is phi, okay? Y prime and Y are the same. I'm sorry, Y prime and YB are the same. And then we have some angle XB. Okay? So now if we just look down the Y prime axis, the Y prime YB axis where we did the rotation, right? Then we have this Z prime. Well, let's use a different color. We have Z prime, X prime, ZB, XB. And so here our goal is to write XB in terms of the X primes. Right? So this is phi. So what do we have? XB. How about cosine phi X prime? Plus, minus phi Z prime. YB is equal to Y prime. That's the axis we did our rotation about. ZB is equal to sine phi X prime plus cosine phi Z prime. All right? And if we write that in matrix notation, we have that XB, YB, ZB is equal to cosine phi 0 minus sine phi X prime, Y prime, Z prime. Right? Everybody okay with that? Is there any questions? So we just did two independent rotations, and we introduced this sort of intermediate coordinate frame, the X prime frame. So X, Y, Z is our geographical coordinate system, which you might also call northeast down. Okay? And we introduced X prime, Y prime, Z prime, which was a rotation about the Z axis by delta. And then from that X, Y, Y prime, Z prime, we rotated about the Y axis to get into our borehole coordinate system, okay? And that was a rotation about the Y axis by phi. And so now we have two sets of equations. We have one that takes the X primes into the boreholes, and one that takes the geographic into the X primes. But these are just equations, right? If you notice, what if I just plug in this here? Then I have a system of equations that takes me from the borehole all the way back to the geographic coordinate system, right? And so if we write that out, we have this. And we know how to do matrix-matrix multiplication, right? So let's multiply this guy together. So what's the first term? Let's call this A and this B, right? We take the first column of B and dot product with the first row of A. So what do we get? And we take, for the second term, we take the dot product of the second column of B with the first row of A. We get that. Then we take the third column of B with the first row of A. We get that. And then we go back, we're going to take now the first column of B with the second row of A. Second column of B, second row of A. This is delta, sorry. And then third row, third column, second row, it was 0. Then we go back, we have first column, third row. Second column, third row. Third column, third row. All right. So this we'll call RB. So this is a rotation matrix that takes us from the geometric coordinate system into the borehole coordinate system. Okay? So the rotation matrix that you saw the other day that takes you from the principal stress to the geometric was formulated the same exact way as we did here. It's just there's a third rotation. So you'd have to introduce a second intermediate coordinate frame. So you introduce an intermediate coordinate frame, you perform one rotation. You introduce a second intermediate coordinate frame, you call it X double prime, Y double prime, Z double prime if you want. Introduce a second rotation, and then finally the third rotation. So then you have 3 matrices, and then you multiply those all together, and you'd have your final matrix.